A very warm welcome, my dear students. In today's video, we will study about current electricity, and the topics that we are going to cover are electric current, drift velocity, relation between the drift velocity and electric current, Ohm's law, and resistivity. Let's start working on electric current first. So electric current is the rate of flow of charge. How quickly, how much amount of current flows in a circuit is what is electric current. Now, current is given by charge by time. Charge generally we would be measuring in coulombs. Time would be measured in seconds, and the unit, the SI unit for current is ampere. Many a times we also write it as amps. And the symbol, of course, is just a capital A. So 1 ampere of current is same as 1 coulomb of charge flowing in 1 second. Now, because the charge is quantized, therefore the total charge that any conductor has would be equal to N times E, where N represents the number of electrons that are flowing inside the conductor, or more appropriately the number of free electrons, and E represents the charge on an electron. Now we already know that the charge on an electron is going to be 1.6 into 10 to the power negative 19 coulombs, and of course it's a negative charge. Now, if you want to measure the current in the circuit, generally the device or the instrument that we use is what we call as an ammeter. The symbol of an ammeter is very easy. It's a circle with a capital A inside it. Now, by default, by convention, we say that the current flows from the positive to the negative terminal of the battery. So, by convention, the direction of current is from positive to negative. But if I talk about the electronic current, or if I talk about the electrons flow opposite to the direction of current, or in other terms, they flow from negative to the positive. See, basically initially it was thought that the current is due to the positive charges. That's why we assume that the current is going from positive to negative. But later on, when electrons were discovered, we realized that it's the electrons that are moving and not the positive charges. And that is the time we came up with the convention that, okay, let the conventional current flow from positive to negative and let the electrons continue to flow from negative to positive. That's why we say that electrons flow in opposite direction to that of current. Okay, so this is all that you need to know about electric current. Because your charge is quantized, therefore we can also write the current as, because I is equal to Q by T, therefore I can also write Q as NE. So this can also be written as NE by T. So if you want to find out the total charge, you can use N times E to calculate the charge. That's all about current. Now let's move on to something much more important, that's called drift velocity. What exactly is this drift velocity? We will try to understand that. So let's say I have a conductor, okay? Now inside a conductor, there would be free electrons which are randomly moving in all the directions. Maybe this electron is going here, this electron is going here. So all these electrons would be randomly moving in all the directions. Now, because these are moving randomly in all the directions, therefore they suffer multiple collisions. Now, whenever they suffer a collision, they lose their energy. There are multiple collisions, and since we assume that the electrons are moving in all the directions randomly, therefore if I take in the average velocity of these electrons into account, then the average velocity here would simply be equal to u1 plus u2 plus u3 and so on up to un. So I assume that one of the electrons is moving with the initial velocity of u1, second one is moving with u2, third one is moving with u3. But if I take the average of all these velocities, then that will come out to be 0. Why is it 0? Because electrons are randomly moving in all the directions. So for every electron that's moving towards left, there can be an electron moving towards right. So on the whole, the average velocity is 0, and therefore they do not give rise to any current. Therefore, they do not give rise to current. But but the very moment I apply a potential difference. But when a potential difference is applied, that means the time when I apply a battery there, that time what happens is that these electrons, they all gain energy. Now there are electrons inside it, so obviously they have an electric field. Now due to that electric field, when we apply a potential difference, all the electrons start moving in one particular direction. They start moving in one particular direction. Now, with the moment they will start moving in one particular direction, it will give rise to current. When electrons move in one direction, that gives rise to current. So that means without a potential difference, although my electrons were moving, but because they were moving randomly, therefore it did not give us any current. But when we applied a potential difference, the electrons started to move in one particular direction, and that is why we got a current. Okay, now in general we know that if we apply a potential difference of V, and if I assume the length of the conductor to be L, then this electric field and potential difference can be related as E would be equal to V by L, where V is the potential difference applied and L is the length of the conductor. Also, apart from this, I also know that the force that would be experienced by these electrons would be equal to negative EE, where E is the small e is the charge on the electron, capital E is the electric field. There is a negative sign because it's a negative charge, and because I know that force is equal to mass times acceleration, therefore from here I can say that the acceleration of each of these electrons is E by m. This is the acceleration that is experienced by every free electron inside the conductor. Now, due to this electric field, the free electrons are accelerating, okay? Now, due to this acceleration, of course, they start acquiring a velocity. The average velocity initially without the potential difference was 0. But after I applied the potential difference, the average velocity started to increase. Why? Because the electrons were accelerated. Now they continue to get accelerated till the time they do not suffer a collision. The moment the electron suffers a collision with another electron or the positive ions, that time its velocity drops to 0, and then it has to start gaining the velocity all over again. It has to start increasing the velocity all over again. So over here, now when this is happening, right, when we are talking about drift velocity or electrons is gaining a velocity and then the moment it collides it goes to 0. So what I can say is that this velocity, like let's say for any first electron, now this electron number 1 was moving with some initial velocity u1, like when there was no potential difference. Now after I applied a potential difference, it suffered an it got accelerated and its velocity increased. Now let's say it was accelerated for some time tau, because the moment it will suffer a collision, the velocity will drop to 0 again. So I can say that the new velocity of this electron v1 would be equal to u1 plus a times tau, where tau is the time for which it is accelerated. And I have directly used the equation v is equal to u plus at. So it's something very basic over here, right? Now further, all the electrons, now this was for electron number 1, now I can have for electron number 2 also velocity u2, and that will give rise to v2, which would be u2 plus a tau. The acceleration is same, and tau 1 be the time for which it was accelerated, let tau 2 be the time for which electron number 2 was accelerated. Like this, for any n electrons, I can write my Vn as un plus a tau n. This is the average drift, or this is the velocity or that is acquired by the nth electron. But then I have to take the average of all these velocities. If I take the average of all these velocities, v1 plus v2 plus v3, so on till vn, then I have to divide it by n in order to average it out. So what I can do is I can substitute the value of v1, which was u1 plus a tau 1 plus u2 plus a tau 2, so on up to un plus a tau n, and this all divided by n. Okay, now we are going to do a little bit of mathematical manipulation over here. Let's take all the u1s together. So u1 plus u2 plus u3 so on up to un together by n. Okay, plus I'll have a tau 1, or I can take a also common, so tau 1 plus tau 2 plus tau 3 so on up to tau n divided by n. Now from the previous slide we already know that the average velocity was 0. So because the average velocity is 0, therefore I can write this value as 0. Okay, now the average taus, I can assume them to be just tau. Like the average of this, I can assume it to be tau. So my Vd is equal to simply a times tau. And from the previous page, my acceleration had come out to be minus EE by m. So this is minus EE by m times tau. So this is my drift velocity. That is what exactly is drift velocity. Now let's come on to that part here. See, it is the average velocity with which your free electron in a conductor got drifted under the influence of an external electric field that was applied there, and we denote it by Vd. So this is the expression for drift velocity. Now this is something very important, and you have to keep in mind that, see, when it's like, what exactly does drift mean? Drift means moving under the influence of something. Like, when you have a flowing water body, if you put a paper boat inside it, then the paper boat also flows along in the water body. So this drift is exactly the same thing. The moment you apply the potential difference, due to the applied electric field there, the electrons start flowing under the influence of it, and the velocity, the average velocity that they acquire during that time, is what is drift velocity. Now, as I told you earlier, that the electron would be accelerated only for that time duration till the time it's not suffering a collision. The moment it suffers a collision, the velocity drops to 0. So the short time for which a free electron accelerates before it undergoes a collision with a positive ion is what we call as relaxation time. So this tau over here is nothing but the relaxation time. And I've taken the average of all the taus, so it is the average time. So it's the average time for which the electron is accelerated. So over here we have derived a relationship for drift velocity. Now we would want to try and relate this drift velocity to the current, because obviously if the electrons are flowing, that they are going to give rise to a current. So let us try and find out a relationship between the drift velocity and the electric current. So over here, let's assume that the length of my conductor is still L, okay, and the area of cross section of the conductor is A. Now I already know that if I want to write down the volume of the conductor, then volume of the conductor can be written as the area of cross section times the length of the conductor. So this would be A times L, that is AL. And we also assume that small n is the number of free electrons per unit volume. Now, if I want to find out the total number of electrons, then that can be found out by multiplying the number of free electrons per unit volume with the volume. So the total number of free electrons will be equal to n times the volume. And the volume I have just figured out is AL, so this is n times AL. And now if I want to find out the total charge that is coming due to the free electrons, then that would be the number of electrons times the charge on one electron. So NaL times E, where E represents the charge on one electron. Further, now over here, if I want to write the current, in general, we wrote that current was equal to the total charge by time. So charge here is NaLe, and let the time be t. Now since we already derived an expression for Vd, so I know that the average drift velocity can also be written as the total length by the time, right? Or we can rearrange this for time. Time can be written as L by Vd. So if I substitute this value of t in here, what will I get? Let's try and understand. So my I would be equal to NALE and T I am writing as L by Vd. The LL gets cancelled and my current comes out to be equal to NEAVD. Now this is the relationship between current and drift velocity. Vd represents the drift velocity, I represents the current, small n represents the number of free electrons per unit volume, E represents the charge on an electron, and A represents the area of cross section. Now, so we have understood what is drift velocity, we have understood the relationship of drift velocity with electric current. Now we move on to the Ohm's law. Now for Ohm's law basically gives us a relationship between the potential difference and current. Now it simply states that the physical conditions like temperature, mechanical strain, if they remain unchanged, then the current that is flowing through a conductor is always directly proportional to the potential difference that is applied across its ends. That means greater the potential difference, greater would be the current, or vice versa is also true. To remove this proportionality sign, we introduce a constant, and the constant here is R. So V is equal to IR, where R represents the resistance. See, the potential difference would be measured in volts, I would be measured in ampere, and the resistance has to be measured in ohms. The symbol for ohm is the Greek letter omega. If I draw a graph between I and V, then that graph comes out to be a straight line. That is what is true for Ohm's law. For any ohmic conductor would be the one that obeys Ohm's law. The graph would be a straight line like this one. From this graph, if I calculate the change in I by change in V, that means if I take the gradient of this graph, then that will give me 1 by R. So the steeper the IV graph, the lesser would be the resistance. Now, what exactly is this resistance firstly? So see, resistance is simply the obstruction to the flow of current. So resistance is the obstruction to the flow of current. Your current is trying to flow, but then because it collides with the other electrons and it also collides with the positive charges, so that time the path of the charge is obstructed, and this is what is resistance. So resistance is the obstruction to the flow of current. Now V is equal to IR, but R in this equation is just a constant of proportionality. Therefore, a very, very important point that you have to keep in mind is that your resistance is independent, always independent of V and I. Your resistance increases or decreases, it can affect the current and the potential difference. But if you double the current, nothing happens to the resistance. You triple the potential difference, nothing happens to the resistance. Your resistance remains independent of V and I. Further, this Ohm's law that we just learned tells us that the VI graph should be linear, which is true for a metallic conductor. But there are situations when the Ohm's law fails. When does it fail? When your potential difference varies non-linearly with current. If the potential difference varies non-linearly with current, such devices are called non-ohmic devices because they do not obey Ohm's law. Why they do not obey Ohm's law? Because for them V and I is not proportional. See, V and I are proportional and R has to remain constant. If you look at this graph over here, you can see that here in this part of the graph, it no longer remains linear. Why? Because probably due to heating, the temperature changed. And if the temperature changes, the resistance also changes. Because over here you can see that when we define Ohm's law, we said that the physical conditions are supposed to be kept constant. But there is a possibility that the physical conditions could not remain constant due to the overheating of the device, and therefore the graph gets deviated from its linear path. So this one is non-ohmic. If you look in on the graph here on the right, again you can see that there is no linear relationship here between V and I. So because there is no linear relation here between V and I, and you can see that here the current increases rapidly, then here there is almost no current at all. This graph is basically for a diode, okay? But a diode is firstly not a metallic conductor. A diode is generally made up of semiconductors. So it does not obey Ohm's law. So it's a non-ohmic device. This one here at the bottom also is the graph of a thyristor. Again, it's a non-ohmic device because you can see that the graph is not a linear one. The V and I are not proportional to each other. They do not have a linear relationship. So there are devices that do not obey Ohm's law, or the devices for which V and I are not linear. Okay, so there are some exceptions to the Ohm's law as well. So if you understand this, then let's move on to resistivity here. So what exactly is this resistivity? How are we going to understand it? Let's talk about that. So I told you that your resistance does not depend on the potential difference and current. Then what are the factors that affect resistance? Now for the factors that affect resistance, the first one is the length of the conductor. The resistance of a conductor would be directly proportional to the length of the conductor. Why is it directly proportional to the length? So I told you that resistance is the obstruction to the flow of current. Now the longer the conductor, more is the possibility that the electrons collide, and more your electrons will collide, more would be the resistance. So resistance is directly proportional to the length of the conductor. Also, resistance is inversely proportional to the area of cross section. So why is it inversely proportional to the area of cross section? Because the thinner the wire, the more is the possibility to collide, and the thicker the wire, because there is more space available, that's why the probability to collide decreases, and hence the resistance decreases. So the greater the area of cross section, lesser would be the resistance. The third factor that affects resistance is actually the nature of the material, like if it's a good conductor or a bad conductor. And apart from these three, temperature also affects resistance. But then mathematically only these two are generally taken into account along with the resistivity, which I will talk about now. See, if I combine these, I have resistance directly proportional to the length of the conductor by area. To remove in the proportionality sign here, and bring in equality, I have to again introduce a constant, and my constant over here is rho. It's a Greek letter and it represents resistivity. Resistivity is also called specific resistance. What is the specific resistance, or what is this resistivity? Let's understand that. So firstly, this resistivity would be measured in the units of ohm meter. And then if I assume that the length of the conductor is 1 meter and the area of cross section is 1 meter square, then my resistance would be equal to rho. So I can say that the resistivity or specific resistance of a material of conductor is the resistance that is offered by a wire of this material of unit length and unit area of cross section. Unit simply means 1. So if I take the length as 1 and the area of cross section as 1, then my resistance equals to resistivity. Over here we have this factor of rho, or I have specific resistance or resistivity C. Resistivity depends only on two things. Firstly, it depends on the nature of the material. Again, if it's a good conductor, the resistivity would be less. If it's an insulator, the resistivity would be high. Then resistivity also depends on the temperature. Now we will talk about the dependence of resistivity of temperature in detail in the coming few minutes. But before that, let us go into the details of the factors that affect this resistivity. So, for the factors that affect resistivity, we will try and do a small derivation, a very easy one. So I already know that my drift velocity is given by E by m tau. This is the expression that we had derived in the previous few slides. And then I also know that my current is equal to NEA VD. So these both expressions we just derived. Now what I'm going to do is I'm substituting this value of VD here. So my current can be written as NEA, and instead of VD we write EE by m tau. I have replaced VD with this. If I further simplify this, my current comes out to be NE square AE tau by m. I also know that my electric field can be written as V by L. Therefore, the current can be written as NE square A V tau by M and L. Okay. Now, on further simplification over here, I can take V by I to the other side, or I can rearrange this expression to give me V by I. So, V by I would give me ML by NE square A tau. Now V by I we know is nothing but resistance. So this expression is equal to R. Now just now we had also written another expression that R is equal to rho L by A. So instead of R I can write ML by NE square A tau, and this is equal to rho L by A. I rearrange this expression to get rho, which would be equal to MLA by NE square A tau and L. So A and A get cancelled, L and L get cancelled. So my rho from here comes out to be M by NE square tau. This is the expression for my resistivity or rho. Now from this expression we can conclude certain things. First one, over here you can see that my rho is directly proportional to the, my rho is directly proportional to M, or more appropriately you can see that my resistivity depends on the number of free electrons, right? The number of free electrons per unit volume, and my rho is also inversely proportional to tau. So it depends on the relaxation time and the number of free electrons per unit volume. These are the two factors that affect resistivity. That is why we say that resistivity depends only on the temperature, and it depends on the nature of the conductor and the temperature. Those are the only two factors that affect resistivity. Now lastly, we are going to talk a little about the temperature dependence of resistivity. But before that, let me also define conductance and conductivity for you. See, the reciprocal of resistance of a conductor is called its conductance. See, conductance is represented by G, and it is simply the reciprocal of resistance. So it is 1 by R. And conductivity is represented by sigma, and it is going to be the reciprocal of resistivity. So conductance is 1 by R, conductivity is 1 by rho. So these are just reciprocal of resistance and resistivity, just basic definitions, and this formula is all that you need, no more details required. Now let's go on to the main part, which is the temperature dependence of resistivity. See, for the temperature dependence of resistivity, we will talk about three different materials. The first one being a metallic conductor. Now, for a metallic conductor, what happens is that here, for a metallic conductor, the resistivity increases with the increase in temperature. You can see as the resistivity increases, the temperature increases. Why? Because in a metallic conductor, as the temperature increases, the number of collisions increase, and greater would be the number of collisions, more is the resistivity and resistance. So this first graph that you see is for a metallic conductor. The second one over here, this graph, is for an alloy. Now the alloy can be like that of nichrome. Okay, so sometimes in the exam there's a possibility we tell you that draw the graph for the temperature dependence of resistivity for nichrome. So you have to know that nichrome is an alloy, and for alloys the resistivity is almost constant. It is almost independent of temperature. So from the graph you can see that it is changing, but if you see, the change is pretty less. So from almost 0 Kelvin to 800 Kelvin, it has not even increased by 0.1 into 10 to the power minus 8. So you can see the effect here is negligible. That is why the alloys are generally used to make resistors, because then the resistance would remain constant with the increase in temperature. So this is a very negligible change from 1.1 to not even 1.2 when you raise the temperature by 800 Kelvin. So that's a huge constant value. And then this third graph is there for a semiconductor. It can work for a semiconductor and it can even work for an insulator. Semiconductors can be like silicon, germanium, right? For them, the resistivity increases with the decrease in temperature. So for them, resistivity is inversely proportional to temperature. Why? See, a semiconductor doesn't have free electrons. So if it doesn't have free electrons, it doesn't conduct. But then the moment you give it temperature, the moment its temperature starts to increase, free electrons start getting generated and they start moving. So something that did not have a current at all has started to achieve some current. Therefore, its resistance and resistivity both start decreasing with the increase in temperature. All these three graphs are very important. We can ask you that draw the graph for a metallic conductor, draw the graph for an alloy or a semiconductor. So these graphs are there in your NCERT textbook. So do learn them for your CBSE exam. With this, we have completed all the topics that we had to learn today. I hope you understood and enjoyed the video. Please do subscribe to my channel and stay tuned for Current Lexicity Part 2, which will be coming on next Thursday. Thank you.